Oh, there you go. Oh, that's it. On Saturday, one person started to be at the gardens. In a couple of hours, we were 10 of us. We had fire from 3 to 9 o'clock. When most students were worrying about their finals, there were 9, 10 students there. They would not worry about their finals. And actually, these 2 people were there, and there were some other one. Who is the other one to play?
He's not here right now.
Not yet? The guitar. We are missing the guitar. But they made such a beautiful music. There was a girl also who was singing. I'll show you after a few minutes, 2 to 3 minutes, what was happening there. And we made such an incredible music and laughter that was just ecstatic. I'll show you after. Maybe we'll achieve that one there. I don't know if we'll achieve that one. But help us in faith. You have to count?
So I'm going to kind of play Viva La Vida, quickly. So if anyone knows it, try to sing it. If only you want.
The walls were closed on me, and I discovered that my castle stand upon pillars of salt and pillars of sand. I hear Jerry It was a wicked and wild wind, blew down the doors to let me in, shatter when people couldn't believe what I'd become. Revolutionaries wave, for my hand on a silver It's the puppet on a lonely string. Oh, who
we create our world with our thoughts. Whatever our destiny is going to be tomorrow, it comes from our thoughts, the way we develop what thoughts we have, what thoughts we choose to have. Okay, well then, let's continue now. To go into some more problems. Right? I would ask people that they think they know the stuff to move to the back, so you will not have continuously to get up and leave until we are done. Another 40 minutes or something. Half an hour, how much it remains? 40 minutes. Because when people get up continuously, the people that they want to follow, they will not be able to do it. So please, if you are to leave, you should do it now, or if you want to leave later, go on the back. So we're going to have 40 minutes quietness. Okay?
I really need to pass this class.
Okay, so you sit on the back there and you can leave anytime you want. All right, now, let's do this molecular structures. Going to be a big problem there by the points. So let's do that, right? They can be molecules. They can be anions or cations. Really doesn't matter. Their work that you do is the same. So let's take a molecule as sulfate tetrafluoride, and let's try to answer some questions. Okay? So the first thing, usually the table will give you is 2 or 3 of them, different chemical species. Usually will give you with one central atom, a number of terminal atoms, and we ask you to find the electron group geometry, the molecular geometry, the ideal bond angles, oxidation number of some atoms, formal charge, and if it's polar or not. Okay, so let's do this problem really good, so then you can know how to work. So the first thing to answer, in order to answer all these questions, really the first thing to do is to write a correct structure, right? So, in order to do that, we start with the total number of valence electrons. So I have one sulfur, 1 times how many valence electrons of sulfur? Sulfur is on the 6th group, so it has 6 electrons, valence electrons. That means we have 6 electrons from sulfur. Then we have 4 fluorine atoms. That means 4 times each fluorine atom is on the 7th group. That means 7 valence electrons. And that means 28 electrons total from fluorine. And so the total number of valence electrons is going to be 34. And then we make it into pairs. That will be 17 pairs. If I make a mistake, please let me know in advance so I don't have to go farther. Okay, so we have the total number of pairs, total. That's total. To arrange around the atoms, right? Now, the next step is to write this one in such a way to show the connectivity of atoms, right? And like I said, usually we give you simple examples. There is a central atom, it's sulfur here, of course, because fluorine is going to be always with one bond. It cannot be a central one to be connected with many, right? So sulfur will be the central one. Another rule is center is usually the least electronegative, so the most electronegative go on the side. So it's going to be 4, right? 1, 2, 3, 4. Oops. 4, right? To connect the fluorines, right? 4 of them. Single lines. 1 pair of electrons, right? Used. This is the connectivity of atoms. By doing this, for the connectivity of atoms, we already use how many pairs of electrons? 4. That means minus 4 will be how many left? 13 left. 13 left. Available, in other words, to use for each atom in order to have at least 8. Okay, we have 4 fluorines, and each one has 2. As you can see, each one has 2. And if I want to have 8, then I need 3 for each. Times 4, 12. So I need 12 electrons to satisfy all the fluorine atoms in order to have each one of them 8 electrons. Yes? I need how many? 12. And then I will have minus 12, I will have 1 left. So here is the 12. I mean the 12 pair of electrons from the 13 available that I'm going to use for the fluorines. Now each one of them has 8. And I still have 1 left. Well, if I have 1 left, I cannot throw it away. It has to be there. So, since fluorine is, as you can see, on the second period, it cannot have more than 8 electrons. Right? Because second shell does not have d orbitals. And it's only sp. It can go on up to 8. That's why I cannot put it on fluorine. But sulfur has d orbitals, because sulfur, as you can see, is on the third period, which means the valence electrons of sulfur, they are in the third shell. And third shell has d orbitals and can take more than 8. So I can put them there before on the sulfur. And that way sulfur will have actually 10, as you can see. But that's fine for the reason I explained to you. So far, any question? Because if we do this really good, we don't need to make many examples, okay? Maybe another one. So now we can answer every question we mentioned before. The first thing we ask ourselves is how many electron groups? So the first thing we need to answer is the electron group geometry, right? How many electron groups around sulfur do you see? How many? Loud. 5. 1, 2, 3, 4, 5. 5 electron groups. Well, when you have 5, then you have the trigonal bipyramid. You have to remember that, right? So here's one axis, here's another axis, here's another axis. These 3 axes, they're making a plane vertical to the plane of the paper. Yes? And then you have these lines on the plane of the paper. Can you imagine a plane that makes up, these lines make up that plane, vertical to the plane on the paper, and therefore it's vertical to this line? Can you imagine that? All right? Now, we have the 5 electron groups, and the electron group geometry, the 4 electron group geometry is going to be trigonal, bipyramidal, right? One pyramid like this, trigonal, and another one like that, same base. triangular bipyramid, right? Okay. That's the electron group geometry. To find the molecular geometry, which is defined only by the relative position of nuclei of the atoms, not electrons, we have to do the first step. What's the first step? To place the number of electrons that did not participate in bonding in the correct position. And we have trigonal bipyramid electronic structure. Always the pair of electrons that did not participate in bonding will go and occupy the so-called equatorial positions. Yes? That's the only really example you need to worry about, because everywhere else you go, the positions for one pair of electrons is equivalent all everywhere, so it doesn't matter where you put it. But this one only that has axial, 2, and 3 equatorial. And then, so the rule is, you do not worry about where the atoms go. Always you start with the electrons, where the electrons will go. So therefore, one pair of electrons will go in an equatorial position on the plane of these 3 axes. So it doesn't matter where you put it, here, there, there. It doesn't really matter where you put it, right? So I'll put it here. And then we have 4 fluorine atoms, and they will occupy the rest of the positions. So here is fluorine. That's it. Correct? So now, what you do is, you want to figure out the molecular geometry. You hide this because electrons, lone pair of electrons, do not define geometry. What defines geometry is the position of the nuclei of the atoms. And you use one here, one there, one there, one there, and one there. The position of this will define, the relative position of this will define the molecular structure. And as you can see, in order to make it look nicer, this one, you can imagine it point out towards you, and this one goes on the back of the paper. Can you see that? So the structure is really, if you rotate it like this, it's called what? Seesaw, right? When you were little kids, you were doing that. Sitting here, the other guy was sitting there. Sometimes you will do like, bang, like this, or just fall down, right? Okay, so it's a seesaw molecular structure. Okay. Now, next question. For the central atom, what kind of hybridization? What's the hybridization of sulfur atom? Remember the table. If you have 2 electron groups, you have sp. If you have 3, sp2, blah, 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 right? You remember that? The number of electron groups is giving you the total number of atomic orbitals you hybridize, and you start with S, and you use as many as you need. So how many electron groups do we have here? 5. Therefore, we need 5 atomic orbitals. You need 1 S, then in order to have 5, you use the 3p orbitals, you still need 1 more, and that will be D. So the hybridization is going to be sp3d. Everybody got it? Okay, now the next question that you can be asked is to say if this molecule is polar or non-polar. The lone pair of electrons do play a role, but usually it's insignificant. So usually ignore them. But sometimes if you ignore them, you get their own result, their own answer. But usually you can ignore them. Well, let's talk about the ideal bond angles first, before polarity, right? So what are the ideal bond angles? Ideal bond angles means that if you have all of the positions occupied by atoms, all the atoms identical. So if you have another fluorine here, then they will be all occupied, all positions occupied, and all of them identical atoms. Then the angles that you would see by doing X-ray picture, it would be the so-called ideal bond angles, right? So you assume that. What would be then the ideal bond angles? Well, how much this angle would be, how much this would be, and how much this would be. Right? Ideal bond angles. So this one would be what? How much this? 90. And how much of this? You see? But because now this pair of electrons is pushing these pairs of electrons in like this, like umbrella closing, right? The real angles will be, this angle here will be larger than 180, or you can say this one will be less than 180, because it closed a little bit, right? And this one is going to be less than 120 degrees. And this one here, instead of being 90, is going to be actually less than 90 degrees. Because everything is closing like this, right? But we don't ask about that. We ask you, what are the bond angles? Or we'll ask you approximately what the bond angles are. And you put the ideal bond angles, right? So now we can ask the question. What question did we say we're going to ask? Polarity. So the question, next question is this molecule polar, right? Well, even if you assume that you have ideal bond angles, that you don't, even if you assume it's ideal bond angles, as you can see, you will have polarity. Why? Because this dipole moment and this one, there are like two forces, right? Delta minus, delta plus, delta minus, delta plus. You have two vectors like this, equal, straight, if you assume ideal bond angles. They will cancel each other, right? But these two, they will give you a total dipole moment, yes? And it is impossible that that one will be equal to this one that comes because of the lone pair of electrons, because that's a little one, small one, right? If you have an atom here, and you have a lone pair of electrons, you have delta minus, delta plus, but that dipole moment is really small. It's just a small thing here, right? And it's impossible that one to be equal to the one that comes from here. Okay, so if you assume ideal bond angles. If you don't assume ideal bond angles, it will certainly be polar. Why? Because this with this, it's a little bit like this. So it will give you a total. The other two will give you a total. And that little thing here, there's no way it's going to be zero, the whole thing, right? So you can see really intuitively that this volume is going to be polar, right? And then you can answer questions like what's the formal charge, what's the oxidation number, right? So let's say it's sulfur. Formal charge of sulfur. Formal charge of sulfur is equal to how much? Let's see. In order to do the formal charge, remember in the reader how we do it? Really nice? With circles. You make a circle around the atom, whatever atom. So you take a correctly structure and you can find the formal charge of any atom you want by just making a circle, including the lone pair of electrons and half of each bonding pair. Right? So if we do that, we go around making half of these lines and including the lone pair of electrons, which I didn't. Yes, we go like this, right? Then we count the number of electrons in the circle. How many do we have? If it goes into half, that's one electron here, one there, so it's 1, 2, 3, 4, 5, 6. So I have 6 electrons in this situation, and normally sulfur, when there's no chemical environment, is how many? 6. And here it appears we have what? Did we say 6? Yeah. 6. That means that formal charge is 0. If you want to calculate the oxidation number, you can do it 2 ways. You can do it the way chemists made these rules from high school. You just memorize the way they made the rules. You can do it that way, or you can do it the fast way. The fast way will be, you say fluorine is always -1 times 4 minus 4, because it's all neutral, 0. Sulfur has to have +4. If you do it the way, like I said, the chemists derived these rules, and actually you can find the oxidation number for any atom in any molecule per atomic ion without remembering the rules, which many times you can, unless you really know how to do it. That's why I like putting the reader, and I taught you how to do it. So if you do it that way here, we said that we're going to make a circle now. That circle will include the lone pair of electrons again, yes, but the bonding electrons will go to the most electronegative atom. So these two will go to fluorine, the most electronegative atom. So sulfur does not have them. So all of these, 2 here, 2 there, 2 there, 2 there, they will go to fluorines. So sulfur does not have them. And if it was sulfur with another sulfur will go in the middle. So we'll get one way electron, right? Because it's sulfur-sulfur bond, but there's no. So no electrons from these 4 bonding pairs, right, for the sulfur, only 2. Now, when it's free with no chemical environment, sulfur says 6. It appears as what? 2 here. It appears it lost 4. If you lose minus charge, it becomes plus. So oxidation number is 4. You see? It doesn't matter how you do it, you get it right. This is the way they made the rules. But almost no book tells us how they did it. And it's really quite interesting. Because every organic book tells us how to do the formal charge, but not the oxidation numbers. It's amazing. And it's the same really thing, right? It's very easy to do. This way, if you have a Lewis structure, for electron structure, you can calculate formal charge, oxidation number for any atom which is that molecule or polyatomic ion. Piece of cake. Right? Read it from the reader. Always you'll be able to do it. Right? Let's move into making some, well, some cute things here. Let's see. Let me do some things here. How about this problem? How about this one, number 18? How about number 18? Look at it and see if you can do it. Sometimes things that they are easy, they are hardest to do. Isn't it true? How many? Let me see the numbers and see your hands. 1. So I will say the numbers and you raise your hands. Is it 1 electron? 1. 2. 3. 4. Ooh, you're doing good. Okay. That's good. I'm glad. You figured it out. How many people want me to explain it with your hands? Okay. Look. You can see that n is equal to 2, right? So n is equal to 2, it means how many subshells? How many subshells? 2. 2 subshells. Always the first column number tells you how many subshells. If you have n is equal to 50, how many subshells do you have? 50 subshells, right? All right, now, 2 subshells, when you have 2 subshells in the second shell, what is this? What are these subshells? What are they? S and P. When you have S subshell, always an S subshell, how many orbitals it has? Always the P subshell has any orbitals. Okay, then you say when n is equal to 2 in the second shell, how many total number of orbitals do you have? And you have 4 orbitals. 1 is S, and the other 3 are P. Second shell. Then what's the maximum number of electrons? That they all have minus 1/2. Well, let's see. Here is 1. They have to have minus 1/2, so they have to go all down. Here's another one. Here's another one. Here's another one. Can I have another one like down like this? No. If I put it up, I can do it, but it's not going to be minus 1/2. So the maximum number that we can have is pretty. Huh? Okay. Let's see what else. How about molecule, problem 20 here? How about problem 20? Do you remember what we said? Every time you say triple bond, you have one single bond and two pi bonds, right? Every time you say double bond, it's one sigma and one pi, right? So that's not a bad problem. It's a hard problem. How many pi bonds do you see? How many pi bonds? 1, 2, 3, 4, 5, 6. 6 pi bonds. How many sigma bonds? Anybody got it? How many? Tedious, huh? Ooh. How many? Don't worry if you didn't get it. It's not a big deal. Okay? Don't worry if you didn't get it. It's not a big deal. We have quite a few problems, okay? We have time to do more. Let's see which ones we should do.
Double ones?
Okay, how about this? Let's do this.